The purpose of this video is more on inference for means. And the thing that you should know by now, and I put up plenty of videos ad nauseum in some ways, but what you should know now is if we have an inference, we're making an inference about mu, which is a population mean. The best thing to estimate this value is the sample mean. Now, what happens from there, we have two different conditions that we encounter in statistics when we are taking a sample mean to make an estimate about a population mean. And again, guys, remember, in the inference setting, mu is unknown. So we go out, we collect a sample. It's one of infinitely many. There's nothing special about the sample mean that we collect other than it's ours. It's the one that we're going to use to make an estimate of the unknown population mean. But what we end up with is we end up in a situation where when we again collect a sample mean to make an inference or estimate of an unknown population mean, we get into situations where the population standard deviation is either known or it's unknown. Now, you're never going to see an undergraduate statistics textbook, or you're going to rarely see an undergraduate statistics textbook where this isn't addressed. However, in research, rarely do you know a population standard deviation. So because of that, what I want to do in this video is not only get you prepared for your assignment on my math lab this week, but I also want to investigate a little more closely, a little closer, the situation where we're again making an estimate of a population mean, where the population standard deviation is unknown. Now, guys, when this is the case, what we use, and I've taught this in previous videos, but I want to review just a little bit. What we use is called a t-distribution. Now, a t-distribution has characteristics much like a normal distribution. The mean is equal to 0. But unlike the z-distribution, the standard deviation of this distribution depends on what we call the degrees of freedom. And guys, the degrees of freedom is very, very easy to find. It's just n minus 1. So really, at the end of the day, the only thing we need to know to define the distribution that we're using for our particular problem is the sample size minus 1, which is, again, your degrees of freedom. Now, illustration of that, let's say we want to construct a 95% confidence interval, and let's say that we have a sample size of 62. Well, if the sample size is 62, then it tells me that my degrees of freedom, which is n minus 1, which will be 62 minus 1, my degrees of freedom would be 61. So I will be working this problem, whether it's confidence interval or hypothesis testing. I will be working this problem with the distribution of degrees of freedom 61. So that's the t-distribution that I use to work this problem. Now, if I'm interested in a 95% confidence interval, I want to be able to create my t-critical. Now, I'm going to work a problem here in a minute, and the t-critical is found by using a table. And you know, if you've watched any of my videos so far, you know I'm not a fan of tables. I'm a fan of technology for this level of class. I like the theory and all that, but for this level of class, I'm a fan of technology to create t-critical values, which I'm going to use to illustrate in this particular problem. Now, if I'm finding a t-critical, the way I think about this is I have my focus again on this t-distribution, degrees of freedom 61. I want to find the two values that has a lower bound and an upper bound of the middle 95% of this distribution. Now you can think about, again, the mean of 0 is in the center of our distribution. We have perfect symmetry just like in a normal distribution. So I know that this value over here has to be a negative, and I know that this value over here has to be a positive. The number part, keeping it simple, the number part is going to be the same number, again, because of the symmetry. Okay? Now, how do we do that? Well, what we have to do is we have to realize that if we have 95% that we have kind of accounted for, then we have 5% that's missing. Well, half of that 5% needs to go here, half of the 5% needs to go there, giving me 2.5% on both sides. Okay? So I just need to find the number here from the distribution that has degrees of freedom 61 that has 2.5% of the distribution to the left of it. Well, guys, our calculator, let me grab it real quick, makes this so easy. All right? I go to second function distribution. I come down to the inverse t. And again, what I put in first is always to the area to the left. So I need to put 2.5% as a decimal. So that's 0.025. And then all I have to do is just put in the degrees of freedom, which in this case is 61. So my left bound will be negative 1.996 if I go out to 4 places. So I know this is going to be 1.9996, and this will be positive 1.996. Now, let's say you don't trust me. You're like, well, no, wait a minute. How do I know that that's just the positive of the negative there? Well, if you don't believe me, just try it out. How much area do we have below this point right here? Well, we have the 95 plus the 2.5. So from here down, I have this amount plus this amount, which is 97.5%. So let's put in our calculator inverse t, 0.975 degrees of freedom 61, and you're going to see that we get the same value, but it's just the positive of the negative up here. But you really don't need to do that. You just need to find the one. Remember, understand the properties of the t distribution, that symmetric around 0. So it had to be the positive part of this answer here. All right, gang, what I want to do now is I want to work some problems. I'm convinced that as a professor, I can get all theoretical and all that stuff. But I think students most benefit by seeing problems worked that are similar to the ones that they're going to be held accountable for. So that said, I want to come down here and do preview. And what I've done here in this demo is I've created 5 questions that are going to be very, very, very close to things that that you will work. And I wasn't expecting this question right here, but that's just the way it goes. Let me make sure that I'm doing the right thing here. Yeah. All right. Cool. All right. So the first question, which I'll tell you, I didn't want on there, but oh well. Let's work it anyway. So if you take samples of 40 lines from a random number table and find the confidence interval for the proportion of odd numbered digits, captures 50%, 37 out of 40 lines. Is it the confidence interval or the confidence level you are estimating with the 37 out of 40? Well, guys, that's going to be the confidence level, not the confidence interval. The confidence interval, we use an estimate and we build our margin of error around it. So that's kind of a goofy question. I really didn't intend it to be on there. So, all right, now let's talk about some stuff that I did intend to be here. Okay, a researcher collects a sample of 27 measurements from a population and wishes to find the 99% confidence interval for the population mean, what value of should he use for T star? Now, guys, you can get into these goofy tables if you like, and there's nothing wrong with them. I'll show you how to use this once I show you the easy way. All right, so what I would do to find the T distribution, again, 99%. We've got a sample size of 27 up here, so that tells me that my degrees of freedom are 26. So, gang, what I'm going to do is I'm going to go back over here, and I'm going to work this just like I did before. But, guys, in this situation, my sample size is 27. And I have a 99% confidence interval. Guys, let me check. I just want to make sure I'm not doing anything goofy. So 99% and 27. Okay, cool. So same deal, right? I have this T distribution, which is degrees of freedom 26. Draw my two lines just like I did before. I want to look at the values that capture, if you will, the middle 99%. Now, just like I did before, how much am I missing? I'm missing 1%. So I need half of that, which is a 0.5%, and half of that, which is another 0.5%, to go in the two parts that are missing. So I have 99 plus 0.5 plus 0.5 gives me 100%. I need to find the value, or the values, that kind of capture that middle 99%. Well, guys, what did I do before? Put this value in here as a decimal. Guys, move this over two places. 1, 2, fill in with zeros. So what I'm going to do here is I'm going to do the inverse T. So I have 0.005 to the left. My degrees of freedom are 26. So I'm negative 2.7787. So I know that this is positive 2.7787. Now I don't know how far I need to go out. I'll have to read the problem and see. So it says around to three places, so my value for T. Now, for this, we just use the positive part. The T star, the critical value, is known to be the plus and the minus. So what I'm going to do here to three places will be it looks like 779, right? So let's check our answer. Cool. If he instead decides to use a 95% confidence interval, will the interval be wider or narrower or stay the same? Well, I don't know. What do you think? To get 95%, I have to come in, don't I? Because 95% is smaller than 99%. So what do you think? Is this value going to be bigger, smaller, or equal to that? Well, guys, clearly it's going to be smaller than this. So the interval will be narrower because T star is bigger. That makes no sense. The interval will be narrower because T star is smaller. The margin of error is smaller. That makes total sense. All right, gang, what if you dog ate your calculator? Okay, let's go back. What if you dog ate your calculator and you don't have your calculator to work and you got to depend on this goofy T table? Well, let's just work it, all right? We've got 99%, degrees of freedom 26. All right, so we come down to degrees of freedom 26, and we come down to the bottom and we say that our confidence level that we're seeking is 99%. So I come up to 26. Let's move that over. So I come up to 26. I come up to my confidence interval of 99%, and I see that I get 2.779. All right, yeah, it works. Whatever turns you on there, statistically. All right, gang, let's go to the next problem. So a random sample of 112 women showed that the mean number of children reported was 1.61 with a standard deviation of 1.8. Interestingly, a sample of 112 men showed 1.3 children. Well, I don't think that's anything that's interesting because we know that samples vary from sample to sample. So to see that there's variation there, I don't think there's anything that's alarming. So anyway, find the 95% confidence interval for the population mean number of children for women. Because the sample size is so large, you can use 1.96 for the critical value, which is the same as for the standard normal distribution, if you do the calculations manually. Why am I going to do the calculations manually? Because I think it's goofy. Okay, I see no reason to do that. So let me exit the full screen here. And let me move this over. So what I'm going to do, and what I would encourage you to do, is to use the T interval. All right, go over to stat. So my sample mean is 1.61. My sample standard deviation is 1.8. My sample size is 112. And my confidence level is 95. Simple stuff, boys and girls. All right, so my left bound, right bound, and it looks like it wants me to the nearest hundredth, so that's to the two places. So I need 1.27. Whoa! I gotta do more than just put this in. I have to come up with the correct interpretation. So there's a 95% chance that all numbers of children will be between. That's goofy. You know, that can't be true. B, we are 95% confident that the sample mean number of children, well, that's goofy too, because we know that the sample mean number of children is in our interval because we use that to create our interval. It has to be in the middle. So I'm 100% sure that my sample mean is in my interval. We are 95% confident that the population mean number, okay, now I'm getting closer. So gang, that's what we're estimating. We're estimating the population mean, and there's a 0.95 probability, or we are 95% confident that the value we're searching for is the value that we're estimating is between those two values. So 1.27 up to 1.95. All right, let's check our answer. We know it's going to be right. Those were super cool, right? All right, find a 90% confidence interval for the same situation. Well, again, this is where it gets really easy, and you're glad you used your calculator, because all you have to do here is just come down and change the confidence level from 95 to 90. And again, the interpretation, we're 90% confident that the population mean is between, so it's going to be B for the interpretation. And our left bound is 1.33. And our right bound is 1.89. You know, sometimes students miss these because they can't round. And, you know, I feel sorry for students when they do that. But, guys, I hate to put it this way, but I don't think it's a high-level academic exercise to round this to two places and be asked to look at the next digit, and if it's 5 or bigger, change it to a 3. If it's 4 or smaller, keep that as a 2. I don't think that's a high-level academic exercise to be able to round appropriately, so sorry. All right, check answer, nice work, cool stuff. All right, which interval is wider? Well, the one with the bigger confidence is going to be wider, so we're looking for the statement that says the 95% confidence is wider. Then we come up over here and look for the correct interpretation. So we know that A and D can't be true. So our answer has to be either B or C. So the 95% interval is wider because it has a greater confidence level, okay? And therefore we use a bigger value of T star, which creates a wider interval. Guys, I'm buying into that one because that's true. All right, go to the next one. A random sample of 20 independent female college-age dancers are obtained and their heights were measured. Assume the population distribution is normal. What is the sample mean? Is it above or below 64.5? Well, there's our data. So, we're just going to have to, type that data in. So first thing I need to do is get rid of the information that's in my calculator. So I hit clear enter, okay? And I've just got to type this information in, which is kind of a drag, but it is what it is. I could have already had this typed in, but sometimes when I do that, students won't pause. I think they're more likely to type in the numbers and stay with me if they see me going through this. And maybe I'm just making this stuff up. It's not even true. All right, 67, 62, and 67. Hopefully I didn't make a typo, and if I did make a typo, the calculator will make sure that it tells me. Okay, well, the calculator won't tell me. My math lab will tell me because I'll put the answer in. It won't be the case. It won't be the correct answer. Now, what I'll do in follow up, I'm going to show you how to work this problem using R. Which is kind of cool. All right, gang. So I need to find what the mean of my sample. The way I would want to do that is just go to Calc 1 Variable Stats. I put this information in L1. So it looks like the mean is 63.225. So the mean is, let's just type that in, 63.225. And that is less than or below 64.5. Now, I'm going to be able to check if I have a typo. I'm going to get the wrong mean, obviously. Well, not obviously. I could have two typos and they kind of balance out, but that's usually not going to be the case. So I feel pretty good that I got my values entered in the calculator correctly. All right, determine the null and alternative hypothesis. Now, what we're doing here, some people claim that the physical demands on dancers are such that the dancers tend to be shorter, okay, than the typical person in the population. Test that dancers have a smaller population mean than 64.5. So guys, I'm going down here in my alternative hypothesis and I'm looking for the ones that say less than. Not less than or equal to, just strictly less than, so I know that C has to be the case. Guys, your your null hypothesis is always just equal to, not greater than or equal to. I've addressed that in previous videos, but it's always equal to, and then your alternative hypothesis is a contradicting statement. So we know that's going to be good. What's the test statistic? Well, you can do all this stuff by hand, or you can let your calculator do it for you, and that's what I'm going to do here. So I'm going to go through and I'm going to conduct a t-test. I have my data in L1. The hypothesized value is 64.5. I'll let all the calculations be done using the numbers in L1, and I need my inequality to be less than. So guys, I want this right here to match perfectly with the inequality that's in the alternative hypothesis. All right, so come down to calculate. My test statistic is the t-value, so this is negative 2.65. So check our answer. We know it's going to be right. The p-value is given to you. It says round to 3 places. So if I come out 3 places, that's 7. Because that value is bigger than 5, we'll go up to 0.008. And interpret the results. So since the p-value is, so we're testing at 0.05, which is so less than or equal to the significance level, well, we're going to reject H sub O. Therefore, there is sufficient evidence to conclude that the population mean for these dancers is less than 64.5. All right? So cool. All right, gang. The following numbers are the difference in pulse rate before and after running for 12 randomly selected people. Positive numbers mean the pulse rate went up, which you would expect after you run. Test the hypothesis that the mean difference in pulse rate was more than 0. All right, so what we're looking for is we're looking for the alternative hypothesis that's greater than. So that's not it, 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 but this is it right there. So I know that my alternative hypothesis has to be greater than, and the null hypothesis has to be equal to. The test statistic. Well, I don't know about you, but I'm going to use the calculator. Why? Well, just because I am. It's just easier. So I'll get rid of the numbers from the previous problem. So go hit clear enter. And I need to very carefully type in 20, 11, 12, 10, 14, 9, 0, 1, 11, 39, 2, and 16. Now, the first thing I want to do is make sure I've got the right number of numbers in my data set, because it says up here that I need 12. So I can see right there when I go up to the last that I have 12 numbers. So did I make a typo? I could have. I don't think I did. If it were me and it was an exam, I would go back through, and check every number. Just because I wouldn't want to miss a problem just because I had a goofy typo. Alright, so it looks like to me I got this right. My test statistic, how am I going to find it? I'm going to use the calculator. So, my hypothesized value is 0. I'm using the numbers that I have in L1, and I want greater than. So my test statistic to 3 places is 4.019. Okay, why am I off? 4.019. Okay, let's see here. Oh, to 2 places. Duh. So, well, how did I read that and go to 3? Sometimes you... oh, well. The p-value to 3 places. All right, so that's going to be 0.001. Let me see if I can do this without pulling a bozo moment. All right, so we're going to reject the null. So it appears that the pulse rate is higher after running than before. So since the p-value is less than or equal to the significance level is 0.05 as it usually is, we reject H sub O. So there is sufficient evidence to conclude that the mean beats is more than 0. All right. Guys, that's it. I'm going to put I'm going to go back actually in the next video. I'm going to show you how to work these problems in R. You're going to have an R assignment. I'm going to put up a video this week that's going to show you kind of how you do your R assignment. But the first thing I'll do is show you how we could save this table in Excel. And I've showed you this in a previous video, and actually conduct a test of hypothesis using R. All right. But I think by far the calculator is easier. It's just, you put it in your back pocket and take it with you. And so if you're walking down the street tonight and you need to do a t-test, you're prepared. Okay. All right, guys. That's all I got. Take care.